Hello again. Thanks for joining us on a Q&A edition of Space Nuts. My name is Andrew Dunkley. This is where we answer audience questions. And Daryl is asking, could we witness the birth of our sun? That's looking at old light, I suspect. We also have a question from Rennie, who wants to know what we might solve over the next 100 years in astronomy and space science. Dave is asking about a super Jupiter with a moon the size of Earth. It's a bit of a what-if question. And Cal is asking about whether or not a gas giant could become a star. Fred will be answering all of those questions on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
You'll also be answering the question as to why sometimes when you push a button, nothing happens. Hello, Fred.
That's usually because you've pressed the wrong button.
I pressed the right button, but it didn't do anything. So they used to happen on the radio a lot.
Press a button and nothing happens.
Yeah, because and you know what? It's a quirk of the digital age. When we worked in analog radio, a button was a button until it broke.
Yeah, that's right.
But in the digital age, you press the button and that goes, no, I don't want to do that. No, sorry. Go find something else to push.
Need a reboot.
Yeah, indeed. How you been, Fred?
Very well, thank you. Yes, just relishing being back home and being back into the routine with Space Nuts twice a week.
Yes, indeed. Although it's so close to the end of the year, we're just about to go into summer recess or Christmas, New Year recess. But we won't. I don't think we'll take a heck of a long time off. But we'll work it out. We've got to work it out. Now, I've got 4 text questions, and we get a lot more text questions than we do audio, so I thought we'd bump a few of these off politely. So let's get to our first one. G'day, Space Nuts. When we look up at our space, we're always looking back in time. So when we look at Andromeda, the light that we see is 2 to 2.5 million years old. Could we train our telescopes to see light from 4.5 billion years ago and see our sun being born? My guess is no, but I love the idea of it. That comes from Daryl in South Australia, who is a patron. Thank you, Daryl. Much appreciated. So, if you want to become a patron, and jump on our website and get all the details. And the platforms are Patreon or Supercast or Spreaker or Apple Podcasts. They all do their own versions of patron services. So if you're interested in joining Daryl, that would be greatly appreciated, but it's not mandatory. Okay, this one, I suspect he's right that we probably can't look back at the birth of our sun. It's not as simple as just finding it and going, oh, look at that. That's what was happening, all those billions of years ago. But we can see a lot of stuff that's historical, just about everything, actually.
Yep, that's right. You're exactly as Daryl says, when you look out into space, you're always looking back in time. And that's the trick. So we do indeed see the Andromeda galaxy 2.5 million years after the light left. So we're looking back quite a long way.
That's shortening slowly because ultimately when they merge.
That's right. Actually, and as well, just a quick plug for the Andromeda galaxy while we're talking, it's very much in our skies at the moment. November is the time of year when Andromeda is sort of at its highest. It only skirts our northern horizon here in Australia. But if you're in Europe or the United States or elsewhere in the Northern Hemisphere, it passes almost overhead. And in fact, I was looking for it a few nights ago from Cyprus, but the pair of binoculars that I had weren't good enough to find it among the light pollution of the place where I was looking. So I didn't see it, but I kind of knew where it was. I saw Saturn instead. Never mind. That is that's what happens when you're looking at something that is so far away. The light has taken 2.5 million years to get here. The problem with finding our sun being born is that that happened 4.5, exactly as Daryl says, 4.5 billion years ago. And the sun is only 150 million kilometers away. So we can never see the sun except at any other stage than what it was 8 minutes ago. That's the look back time for the sun. It's about 8 minutes. So when you see the sun, you're seeing it as it was 8 minutes ago, not 4.5 billion years ago. So really, the only way you could do this, and it still wouldn't really work, but if you could find a way of putting a mirror 2.25 billion years from us, looking back at us, and you look in that mirror, then the light from the sun being born will have gone out to the mirror, taken 2.25 billion years to do that, and take another 2.25 billion years to get to now, when we're looking at it and we might see the sun being born. But that is flight of fancy, because it's never going to happen.
Even gravitational lensing probably couldn't bend like that.
No, that's right. That's correct. You're right. Yeah.
Sorry, Daryl, probably not, but great question, and keep them coming. But we are seeing and learning so much from historical light and gravitational lensing, and we even get to witness certain things more than once because the light gets split two or three ways, and we can see something from different angles. It's really quite amazing what's going on out there. And to quote Jonty, it makes my head hurt sometimes to try and think of how this is all working and why it's all happening. And
yeah, that's right. Mine does all the time. But you reminded me of something I meant to mention, because there is a quirky thing. We can look back at some events that took place in the historical past, and what I'm thinking of is light echoes. So, for example, the supernova that was observed by Tycho Brahe, the Danish astronomer, in, I think it was 1572 when he observed that. That has recently been observed again because it lit up dust clouds, which give it a dogleg path. So these dust clouds are sort of 400 light years away, and you get this dogleg path, and the light comes to us again with that 400-year delay. And so we can see what that supernova looked like because the light is still traveling. And you can analyze that with modern instruments and find out what sort of supernova it was. I think we covered that in Space Nuts quite a while ago, but it's great. Light echoes are terrific things.
Yes, indeed. Thanks for your question, Daryl. Let's take a break from the show so I can tell you about our sponsor, NordVPN. With NordVPN, you can explore the web securely and privately no matter where you are, whether you're streaming space documentaries, downloading data from the International Space Station, legally of course, or just browsing from a coffee shop. NordVPN has your back. Fast connection speeds, no data logs, and protection across all your devices, including your smart TV, plus access to content from around the globe. It's like having a wormhole to the internet. Sorry about that. Without the black holes. Haha. Right now, Space Nuts listeners get an exclusive deal, nordvpn.com/spacenuts. Huge savings, plus an extra 4 months free. That is fabulous. nordvpn.com/spacenuts helps you stay protected online and gives you everyday access without any fear that your private data will be stolen. That's nordvpn.com/spacenuts, and don't forget to use the code word spacenuts at the checkout. nordvpn.com/spacenuts.
3, 2, 1.
Space Nuts.
This one comes from Rennie. Knowing the pace at which technology builds on itself, do you think we will have solved the mysteries of what was before the Big Bang, dark matter, dark energy, and the expansion of the universe, let's say, within the next 100 years? Rennie's from California and a regular contributor. Thank you, Rennie. I suspect we'll have solved maybe one or two of those things. Even while you were away, and maybe just before you went, they were starting to sort of waver on the expansion of the universe theory. They were starting to think, well, no, we're probably now looking at a Gnab Gib. So that's now starting to change. The evidence is mounting up to change the probability in that regard. So, 100 years is a long time in terms of science and astronomy development.
Yes, it is at the rate technology is changing now. Absolutely. And I think Rennie asks a really good question. It behoves us from time to time to stop and think, well, what are we going to find out next?
Yeah.
The expansion of the universe, yes, you're right. The most recent observations seem to suggest that the acceleration of the expansion is slowing down. Mm-hmm. And if the acceleration slows down enough, then it might well start to decelerate. And so, yes, perhaps one day, I've forgotten how many billion years into the future it is, it's 40 or 50, I think, we might have a Gnab Gib, a big crunch when everything falls back together. So you're right, that's this is discoveries or what you might call facts about the universe that are constantly being updated. So the Big Bang, what was before the Big Bang, that's always an open question because the general theory of relativity suggests that time started with the Big Bang. And so before might not have any meaning. But there are people thinking, well, maybe that's not correct. We've talked about, explosive phenomena in a kind of continuum, things like gigantic black holes exploding. And if we're in one of them, that might be what we see as a Big Bang, even though that black hole was in space that existed already. This is another idea that I think we talked about a few months ago, Andrew. So that's, how you find the evidence for all those things is the important bit. And at the moment, our perhaps most powerful tools are the cosmic microwave background radiation, the flash of the Big Bang, which is still being analyzed, and gravitational wave telescopes, which might lead us to some inferences about the dynamics of the Big Bang, the way material shifted around. So that's one I think we'll see a lot more emphasis, and we might have new discoveries about it. Dark matter, I hope, will get to the bottom of that within maybe the next 10 years rather than the next 100 years. But it's a problem that's existed for 90 years since Fritz Zwicky first spotted it. So it might still have another 90 years to go. I don't know. Dark energy, that it really feeds into or our understanding of dark energy is basically tied up with our understanding of the way the acceleration of the universe is changing. Because if the acceleration is actually decreasing, as we now think it might be, then dark energy is not what we used to call the cosmological constant. It's not a constant phenomenon. It's something that evolves with time, and that becomes even more mysterious. So I think of all those, dark energy is the one that's going to take us the longest to work out, but I hope it's not 100 years, because I won't be around in 100 years' time, even with the best will in the world.
Yeah. Yeah, I know. But where technology is going, it's just going ahead in leaps and bounds.
Yeah.
Look how quickly artificial intelligence has taken off.
Yes, that's right. Yeah.
What are we going to be able to do in 100 years with telescopes? And there'll probably be telescopes on the moon and Mars, and maybe on a few of the other moons in other parts of the solar system. There'll be more space telescopes than you can poke a stick at, I imagine, and very, very high tech compared to what we can achieve now, which is really high tech in itself. Yeah,
space telescopes are things that are not that prolific because they're expensive compared with ground-based telescopes, and astronomy doesn't really have budgets that are huge, compared with something like defense or education or all of those other publicly funded things. So astronomy tends to be very much picking up the pieces. And something like the James Webb Telescope is an exception that is revolutionary. But it's true that there are other space telescopes coming on stream. The Grace Roman Telescope, which will be launched, I think, within the next year, probably sooner, I hope.
I think I looked up a while back that there are 27 or something in the pipeline.
In the pipeline, yeah. Not all of those will be funded, though. And, so that when you think like the James Webb Telescope got into action, 2022? Is that right? Something like that, thereabouts. The last big thing in optical astronomy and in infrared astronomy was the Hubble telescope, launched in 1990. So, that's like 30 years interlude. But yeah, you're right. As time goes on, I mean, one of the things that is changing, that will actually affect this, is that it's now much cheaper to put stuff into orbit than it was. Partly because of SpaceX being able to reuse its Falcon boosters. The latest record is one that has flown 31 times, which is quite extraordinary. But also we've now got Blue Origin coming into the picture with their successful recovery of their New Glenn booster a couple of weeks ago, which is fantastic. So things are changing. Yep.
Yes, indeed. Thanks, Rennie. Great to hear from you. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
Space Nuts.
Okay, next question. Hey guys, greetings from Dave. He's from Sussex County in New Jersey. I have a pretty quick question in 25 parts. Suppose that a Jupiter-size or sub-brown dwarf planet has a moon the size of Earth. Would the moon necessarily be tidally locked to the planet? Also, would it be possible for the Earth-sized satellite to be in the Goldilocks zone of the super Jupiter? Love listening to your podcasts. It's good stuff. Thanks, Dave. Appreciate it. I like this question because, when you're talking gas giants, sub-brown dwarfs, failed stars, whatever you like, you're getting into some pretty exciting territory.
You are indeed. That's right. So super Jupiters, things bigger than Jupiter, and exactly as Dave says, that would be a sub-brown dwarf. I've got to get my thinking right here. I think a brown dwarf, I hope I don't get this number wrong, but I think it has to be more than 13 times the mass of Jupiter for the low-level nuclear reactions that will power it and turn it into a brown dwarf to actually make much difference to it, to mean that it radiates in the infrared region of the spectrum. In a sense, Jupiter itself is a sub-brown dwarf because it actually radiates, I think it's 50% more radiation than it receives from the sun. So there are nuclear processes taking place deep in Jupiter that actually give off energy. And so something like, if you have something, let's say, halfway between a brown dwarf and a Jupiter, and it's got a moon the size of the Earth. That's the scenario that Dave's postulating.
Yep.
Would the moon necessarily be tidal-locked to the planet? In other words, would that moon, the Earth-sized object, be one that always faced its parent planet? And I think the answer to that is yes, because it's all about mass, this whole gravitational locking of moons around planets, or indeed planets around their parent star, because the same thing happens. It's all about gravity. And if you've got, two objects that are bigger than the ones that we think of at the moment, then I think you would still get the tidal locking. So my guess is that your moon, your Earth-sized moon, would be tidally locked. In other words, it would always face the sub-brown dwarf. And then would it be possible for the Earth-sized satellite to be in the Goldilocks zone of the super Jupiter? So that depends on just how much energy you're getting from it. I mean, the Goldilocks zone of a brown dwarf is much closer to the brown dwarf than it is for a normal star. And maybe you can't get near enough. That might be the answer to that question, that the Goldilocks zone is so close to the super Jupiter that it really is, it's not something that's at all practical. I'm guessing at that, and some planetary specialists might correct me, but I think that will be the case, that you're not going to find the Goldilocks zone of a super Jupiter that's going to be very helpful for life on an Earth-sized satellite of such a star. Work that one out for yourself.
Yeah, you were right though. 13
is it
Jupiter masses.
Yeah. Okay, good.
When you get to, sorry, I put my hands in front of the camera there. 13 to 80 Jupiter masses is defined as a brown dwarf.
Yeah.
And then beyond that is a star, I guess, because it can
Yes.
burn hydrogen or something. Is that it?
That's right. Red dwarf. Yeah.
Yes. So under 13 is basically just a gas giant.
Indeed. That's right.
Yes, right.
Or a sub-brown
Or a
dwarf.
sub-brown dwarf. Yeah.
Yes.
Yeah, it's hard to, So the tidal locking question definitely would happen that way.
I think so.
As Dave said. Great question. Thank you for sending it in, Dave.
3, 2, 1.
Space nuts.
Our final question today comes from Cal. Hi, Space Nuts. I was wondering if a gas giant orbiting a star that went supernova can then subsequently absorb the debris from that star at the end of its life to form enough mass to then form itself into a star. And the second part of my question is if not, can a gas giant have enough mass and gravity for other smaller planets to end up orbiting the gas giant with no star? Is there any example or evidence of this ever happening out there? Thank you so much. Cal from Swansea, New South Wales, in the Lake Macquarie region of New South Wales, just across near the coast from us. I drove through there the other day, actually. Yes. What was it? What's he want to know? Gas giant. A gas giant orbiting a star that goes supernova. Could it absorb enough energy to become a star itself? First part of his question.
So when an object turns into a supernova, it basically blasts debris at very high velocity into the surrounding region of space. And it's not even clear that a gas giant would survive that, let alone accrete debris to form a star itself. So I think the answer to that first part of the question is no. If you've got this gas giant orbiting a star that goes supernova, I don't think it would end up a star itself. It might even end up being destroyed by the shock waves that come from the supernova. On the other hand, we do have one example of a planet orbiting something that has gone supernova, and that was the first extra solar planet that was discovered back in the 1970s, I think. There's something called the double pulsar. I think I'm right in digging that up from my memory. Anyway, a second part of the question, if not, can a gas giant have enough mass and gravity for the other smaller planets to end up orbiting it with no star? So perhaps what you're thinking of here is one of these objects that we call a rogue planet or an orphan planet, something that is going through space with no star. And many of them are gas giants. That's right. They might be what we could call failed stars. And probably they have their own moons, which might, in some circumstances, be the size of smaller planets. We haven't observed any moons of rogue planets or orphan planets yet, but it's possible they might be there. So the last bit of the question, is there any example or evidence of this ever happening out there? I don't think there is, but I wouldn't rule it out. It might well turn up that we see objects in orbit around rogue planets when we've got, probably the next generation of big telescopes.
Yes, indeed. But when it comes to astronomy, it's very difficult to rule anything out a lot of the time because the more exoplanets we discover, the more unusual things we tend to find, like those cotton can planets.
Yeah, that's right. Fluffy ones.
Really huge planets that have got next to no density at all in some respects. They're just like vapor. For want of a better term, and there probably is a better term for that. But there's we're finding, and Jonty and I talked about this recently, and you and I have talked about this, that our solar system's starting to look like it is not typical. When we look at other solar systems and how they've formed and how gas giants seem to be on the interior rather than the exterior, ours seems to have kind of flipped and doesn't look normal at all. We're unique, possibly. I would think in the
which is-
scheme of things we wouldn't be, but it's just looking that way.
But certainly you're absolutely right. We look very unusual. We look a bit conspicuous, really.
Yeah, and we've got one other thing that's really weird that no other solar system's shown us that they've got yet. We've got a planet with life, an abundance of life in a great many forms, from single cells right up to complex life forms. Plant life. The list is long. It's when you really think about it, this planet is miraculous with what it contains. It's
that's right, and that's one of the reasons why why there is such an emphasis on detecting other Earth-like environments to see whether the same sort of miraculous array of living organisms can exist there. And so far, we've drawn a blank.
No, the Drake equation remains at 1.
Yes, it does. That's right. Yeah.
Would finding life on one of the ice moons in our solar system, like Enceladus, change the Drake equation? No, because it was based on life that was capable of communication, wasn't it?
That's right. It is, yeah. And it's basically life on planets around other stars. That's right.
Yeah. So it wouldn't
Drake equation set up. So no change to that.
Indeed. All right. Cal, thanks for the question. Very, very interesting and thought-provoking. And oh, that's right. There was a question that came to my mind from Cal's question. How big a radius when a star goes supernova are we talking in terms of devastation?
You're talking about light years because the shock wave. When you think of like supernova 1987A, which is one of the best studied of all supernovae, it was in the Large Magellanic Cloud, so relatively nearby, 130,000 light years away, something like that. Yes, my numbers are all a bit rusty because of jet lag, but it's something like that, maybe 160,000. Anyway, never mind that; it's a long way off, and it's very well studied, and you can already see the fact that there's high energy radiation gone through a large neighborhood around it, measured in light years, which of course is much bigger than the solar system. So that's the area of devastation. Yeah.
So a planet sort of orbiting a star like that probably wouldn't have a prayer, would it?
Yeah. Yep. That's right.
Okay. Thank you, Cal. Enjoyed that question very much. And if you've got a question for us, please send it in. You can do that through the Space Nuts website, spacenutspodcast.com, spacenuts.io. Click on the AMA link at the top and you can send text or audio questions. Easy to send an audio question because if you've got a device with a microphone like a smartphone or a tablet or a computer, they've all got them these days. Just press and talk. And don't forget to tell us who you are and where you're from. We're all done, Fred. Thank you.
Great pleasure, Andrew. Good to chat and great to get our listeners' questions again. There's some really intriguing thinking going on there.
Indeed. We'll catch up with you real soon. See you, Fred.
Sounds good. Thanks a lot.
Fred Watson, astronomer at large. And thanks to Hugh in the studio who couldn't be with us. We were just talking about gas giants. Well, he's got a giant gas problem. and he's had to go to hospital. But he'll be back soon. And from me, Andrew Dunkley, thanks for your company. We will see you on the very next episode of Space Nuts. Until then, bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.